All right, guys, honestly, I've forgotten how far we got into PowerPoint 1, or even if we did. Surely we did. We were here 2 days last week. So, I wish I wouldn't hide my quick. There we go. All right. I like being able to see this. Okay, I'm going to skip what hardware is. I'm going to skip main memory. I'm going to skip auxiliary memory. I'm going to skip drives. Did I get on the board? And Lindy, I know you've heard the lecture before, but did I get on the board and draw a chip in a box in the memory? That sounding familiar to y'all? Feel free to shake your head no.
No,
Right.
I think you said that you would draw it.
All righty, I said I would. Okay, so you guys watching at home are not going to be able to see this. Sorry about that, but you'll get to hear. That's pretty cool, ain't it? Let me know if I need to turn the projector off for you to see this. If the glare is too bad, I'll turn the projector off. Turn the projector off? You wish it was off? We're all good? Okay. So, how a computer works. We've got a box. We've got a dude named Chip. That's a very punny name, right? Computer, Chip. He's got a little window that he can see out. He's got another little window. Not only can he see out, he can reach out, right? He can write stuff. Or maybe instead of writing stuff here, he's going to have like 3 pieces of paper on the wall here. We're going to call those registers. Like in the old days, they had registries, you know, like you filled in registries. We're going to say that that's register 1, register 2, register 3. All a register is a piece of paper that can hold a number. Now on the other side, he can reach out the window, he can read, and he can write. And he's got like an infinitely long piece of paper. It's got lines on it. Each line is exactly big enough to hold 1 number. And each line is numbered, right? Consecutively. 1, 2, 3, 4, 5, except being a computer, starts at 0 instead. Okay, so Chip can reach outside, he can read the paper, he can write to the paper. That's his memory. We're going to call this RAM, random access memory. Why? Because he can read any address on it that he wants. He can scroll it up, scroll it down, right? It doesn't matter whether it's address 2 billion, he can get to it. That's not the only kind of memory there is, but he can randomly access any point in it that he wants. We're going to invent a little language because we want to give him instructions to do math. So we're going to invent a language that looks like this. It's only going to have like 3 or 4 instructions, so we'll just number them, all right? The first instruction means read. The second instruction means write. The third instruction means add. And the fourth instruction means go to. Those are all the instructions that he needs to know in order to do the math program that I'm going to give him. So here's what I want his program to do. I want him, his first step, to read. I need a little bit more room. To read from 0 and put it into register 1. That's what I want him to do. And then the second task I want him to do is to read from line number 1 on his sheet of paper and to put it into register 2. And then I want him to add register 1 and 2 and store the results in 3. Then I want him to write the contents of register 3 into memory address 1. And then I want him to go back to the top, which I'm just going to say go to 0. 0, like these were line numbers. 0, 1, 2, or maybe this is like line number 10 and line number 20 and 30 and 40 or something like that. He's going to go back to the top of the program. This is his little program he's going to follow. So we could write these instructions up, right? We pull up our notepad, right? And we type in these commands. Now, he doesn't understand English. He doesn't know what read and add and write and go to. All Chip understands is numbers. So when we type this up, we have to run it through a process known as a compiler that's going to translate it into something that Chip can understand, which is numbers. And so what's a read number? It's a 1. 101. What's another read command? It's opcode. These are opcodes, is what the technical name for it is. An opcode is an operation that a chip can execute. And modern chips have thousands of different opcodes so that they can do all sorts of different things. So that's also a opcode 1, and it needs to do a 1 and a 2. So what is the opcode for an add instruction? Here's our list of opcodes. So what is an add? It's a 3. 3 followed by those two numbers, 2 and 3. And then a write is an opcode what? And what would my next numbers be after the 2? If we go over here, what are the two numbers that follow the command? 3 and 1. And the last one is a go to, which is an opcode 4, and it's just going to go back to line 10 or go to the top or whatever. I haven't figured out how I'm going to represent that in the future. Go to beginning. Maybe I should have just called it restart. Okay, let's watch. This is our compiled code. And we send that over to Chip. We say, get to work, do this stuff. He needs some data in here in order to play with. So before we tell him to run his program, we just put some numbers in here. Like we put a 23 in the first line and a 10 on the third line. That's probably enough. Okay, so get to work, Chip. His first command. I'm going to refer back to these because I don't want to have to do the little mental gymnastics of what a 1 means, right? But I could, right? If this was erased, I could look it up and know that 1 was a read command. You know, and 3 was an add or whatever. Okay, so read address 0 and put it into register 1. Okay, address 0 has got a 23 written on that line. Ooh, I love that sound. All right. Next command, read from 1 and put into 2. So what's at address 1?
10.
Next, add register 1 and 2 and stored in 3. Well, 23 plus 10 is 33. And then write out what's in register 3 back to address 1. Well, register 3's got a 33. We're going to come back over here and put that there. Now go back to the top. Do it again. Read address 0 and put in a 1. Well, that's still a 23. Didn't change. Read from address 1 and store it into registry 2. Well, it's no longer a 10 anymore. It's a 33. And then add register 1 and 2 and store in 3. So 23 and 33, 56. Next instruction, write out register 3 into address 1. Well, it's got a 56. Go to top. All right, read in 23 into register 1, read in 56 into register 2, add the 2 together, that's like a 79. Write that back out. You can see what it's doing, right? The number's getting larger and larger. That's all that a computer is it's a piece of machinery that processes numbers according to a specific series of opcodes that are built into it. Now, what's weird is that in modern computers, these numbers are also stored in memory, right? So somewhere else on the infinitely scrolling memory, well, it's not infinite, right? But modern computers have like gigabytes, which is billions of numbers. So who knows? Maybe on line number 2 billion, we have these numbers all in a row, right, written here. And he reads from those. We tell him just to go to address 2 billion and start reading and doing those commands. Older computers did not have their programs stored in the same memory that they did their math on. And that's all that a computer is. It's got some RAM. It's got a chip. Chips nowadays are huge. Back in the old days, they had different kinds of chips, like a floating point coprocessor in order to do math that had decimal points, because a computer treats whole numbers very differently than numbers with decimal points. They're handled completely differently. Under the scene, we don't know that. All we know is that we want to add 2.3 to 4 and get, 6 point whatever. We don't care how the computer does it, but it does it. And then later on, he may have access to some permanent storage, so he could save it out to disk, or he might be able to print the results out, something like that, as our equipment gets more and more complicated and he has the ability to do more and more things. That makes sense? No. I love CHIP. Unfortunately, some of y'all get to sit through the lecture like 4 or 5 times. I'm sure Lindy loves this one. She's been in a lot of my classes. All right, so we've talked about CHIP. The main memory stores our data, our numbers. And by the way, a word is just a series of numbers. Like if I have the word bad inside the computer memory, I'll show you how I came up with these numbers. They're not magic. It's written like this. 4 numbers in a row in memory. 66, 65, 68, 0. And the computer knows, according to the program, that that's the word bad. Well, how in the world do these numbers mean that? Well, it's called ASCII, the ASCII code. If we come up here and we Google up ASCII code, and we find a link, not really what I wanted, that's pretty primitive looking. Why don't we find, I think I'll go to ASCIItable.com. All right, and so a B is represented by the number 66, and an A is represented in computer memory as a 65, and a D is represented by a 68, and then there needs to be a marker to say, oh, by the way, this is the end of the word, and so the last number is a 0. So when your computer or your phone accesses something off the internet, each letter that's on the web page is just encoded into a number that can be sent, over the cell phone, over the network, whatever. All right, so everything is numbers underneath it all, according to a computer, right? A music file is just a series of numbers that get translated into audio. A photograph is just a series of numbers that represent the color of each picture in your photograph. So the so-called CPU is the chip that's the computer's brain. He accesses his main memory. He's got input so that, we can type in stuff from the keyboard, or we can move a mouse around, or we can touch on a screen. And he's got output, like a screen. That's the most common output device, right? But also, the headphone jack, or printer if you hook it up, whatever. So when a computer is performing calculations, often it needs to save the intermediate results. It stores those in main memory. It may also need to save it to a storage device, a disk drive, or a flash card, right? Or on your phone, you don't actually have a disk drive. The old iPads actually had itty-bitty little inch-wide disk drives, but then the later ones had what's known as flash RAM in them. Just like your card, your camera uses. It's the difference between auxiliary memory and main memory is that if you shut your computer off, everything is reset in main memory. But it keeps the auxiliary memory, right? It'd be a real drag if your hard drive gets erased every time your computer turns off. You wouldn't like that. But it does reset the main memory, just like your phone. We don't turn our phones off very often, but when we do, it wipes out all the RAM. But all your programs and data and stuff are stored in auxiliary memory, which is the flash RAM, semi-permanent form. So computers don't understand the alphabet. They only understand ones and zeros, just like I was saying. B, A, D would have been that 66, 65, 68, and so on. Instead, they put different letters, and they're not even showing you the ASCII values, but it's the same idea. In consecutive memory addresses, it has a value for an E, and then for an M, and then a U. So-called RAM, random access memory, is volatile. volatile. It doesn't mean, ooh, it's ready to explode, it's angry, right? Instead, it just means that the data is lost when the power is turned off. Auxiliary memory, like your hard drive, is non-volatile. It says it's storing permanently. Well, I don't know if we came back 20,000 years later if our hard drives would work, but it's certainly a lot more permanent than RAM, which, loses its data as soon as the memory, the electricity's off. So what is a program? It's a series of instructions that can solve a problem. You want to calculate, the number of feet from here to Walmart, or you want to, display a map, or you want to, you want it to display, the Declaration of Independence, or you want it to access the internet. It's going to be a series of instructions that tell the computer how to do all that. It says the first step in writing a program is writing a draft where your focus is on the logic. Now this is fundamentals of programming. We're not going to do anything with pseudocode in this class. Maybe we'll give a demonstration or two. If you get stuck on a program, you can't figure out the so-called algorithm. Ask me for it, and I'm likely to give you the algorithm, which is a series of steps the program needs to do in order to solve the problem. Now it's going to be written very generically. It's not going to be written in Java. Like the algorithm for calculating the inverse of a number might be something like this. Output, enter a number, right? And then input x, and then set y equal to 1 over x, and then output inverse is, in quote, y plus y or comma y or something like that, right? That's my algorithm. That's my pseudocode. I just taught Python, so I put a hash sign there. In our language, it would be that. Now, this is not a programming language. I could not type this in and have it do anything. I, the master program, takes those instructions and turn them into words appropriate to the language. Now, if this is Python, for output, I would do print, right? X is equal to input. Now, and so on. If it's Java, I do something else. System.out.println, quote, enter a number. And then X is equal to, sc.next double, whatever, right? I have to turn this stuff into a computer program. Sometimes figuring this part out is the hard part of the assignment. If you get stuck, I can provide the algorithm. Then if you get stuck again, I can help you on turning it into the actual program. But the difference between the algorithm and the program is the algorithm is just the, the loosey-goosey description of how you would solve the problem. And then the program are the instructions written in the specific language, C++ or Java or Python or C# or whatever. Algorithms are the description of how to solve a problem. They're like the recipe. I can make a recipe for baking cakes, but until I hand you the recipe and tell you to go do it, it doesn't get solved, right? And maybe you don't speak English, maybe you speak French, so the recipe needs to be converted into French before you can bake my pastry. So the algorithm is the recipe, and then the program are the instructions in French, and then it doesn't actually get done until I give you those French instructions. So we have the source code, and then it gets turned into machine language, which can then be run on the computer. You don't have to type all these notes in. I upload them. All right. So this act is known as compiling right here. Source code is so-called compiled into machine language. The machine language is the zeros and the ones, the numbers, the opcodes that tell the chip what to do, right, which runs on the computer. Now this is for a compiled language, like C++. Interpreted languages are a little bit different. Java and Python are interpreted languages.
The compiling is the act of taking those English words, like when I had to read and write and add, and turning them into the numbers. So the way those work is you take your source code, something converts them into an intermediate kind of code, some halfway point, bytecode. And then something else turns that into machine language, but only when you really need to run it. This is the act of compilation, and it creates a file that can then be run on any computer. Now that C++, when you wrote a program, it only runs on the operating system for which it was designed. Like you could write, a game for your Android phone, but it's not going to run on your iPhone. Not going to run on your PC. It's not going to run on your Mac. When something is compiled into an app, into machine language, it only runs on the machine language for that specific chip, that specific hardware. But when bytecode is produced by a language like Java, then there is a layer which can run that bytecode, and it converts it to machine language on the fly. And that layer can be written for your Mac, for your PC, for your Linux, for your phone, whatever. And so something has to turn the bytecode into machine language, which is called the Runtime Engine. So you write the source code, that's your .java file. You compile it, and it makes bytecode, which I think is called an OBJ file. And then you run it, and it gets turned into machine language, which runs on the chip. That's a series of steps that our language follows. Whoopsie. Now that's more complicated than what we think. We just know that we type in something in NetBeans, we click the green button, and it works. Well, what really happens? We type in our code, we click the green button, it's compiled and turned into bytecode. And if we had just done build, then it doesn't actually run it through the runtime engine. But if we click the green arrow, it actually starts it. And it reads that data and actually runs by turning it into machine language, those opcodes which run our chip. The advantage of an interpreted language is that it'll run for any platform that runtime engine can be written on. Just like maybe you're nerdy enough, and I don't mean that as an insult, to have installed emulation software that'll let you play Nintendo games on your computer, right? It's called an emulator. It takes the contents of a cartridge, it's a file known as a binary file, and does all the necessary interaction with your computer to emulate that Nintendo. And you can also get an emulator for your other kind of computer, right? You can get the emulator that runs on Windows and a different program that does the same thing for on your Mac or for your Raspberry Pi or your phone, that lets the same data be run on completely different operating systems. Same thing. Once Java is turned into object code, bytecode, that runtime engine can be written for the Mac, and it'll take that same file and run it, regardless of whether the runtime engine is the one that's supposed to work on the Mac or on the Windows PC or on Linux or whatever, which is different than the source code getting compiled and turned into machine language, stored as an executable, which can only run on a specific type of computer. Windows programs run on Windows machines. Macintosh computer programs run on Macintosh machines. And yeah, if you install extra software, you can run Windows software on your Mac, but again, it takes an extra layer in order to do that. Right. So programming language is the language that gets turned in to those opcodes. A high-level language is one that uses English words like print and input and import and nice words like that. And a high-level language uses nice algebraic expressions like A equals 1 plus 2 or B equals C times X, right? Nice algebraic expressions. There are also low-level languages. A low-level language is one that looks a lot like those instructions that we turned into opcode. Let me show you an example of a low-level language. Hello world in assembly. A low-level language is just a series of instructions that directly correspond one by one to the opcodes. Now, this is a different chip, so instead of read, it's using a so-called move command, but it's just the same thing. Move a piece of data somewhere, move another piece of data somewhere else, move another piece of data. All this is doing, all these lines of code are supposed to be doing is displaying the words hello world on the screen. And instead it had to do these, 10, 15 lines of stuff in order to display the word hello world on screen. Whereas in Python, it'd just be print parentheses hello world, right? One line of code would do all of this stuff. That's because Python is a high-level language. You don't care about all the little details. Assembler is a very low language. It's like zooming in and looking at, the individual grains of sand in the sculpture, or the individual pieces of wood in the furniture. Whereas a high-level, you're just looking at it from a distance, and it's okay. You don't need to know all these details to know how something gets displayed on the screen. It differs from computer to computer, anyways. So, low-level language is like assembly. Even lower is just shows pure numbers, right? That's machine language. Assembly is just little mnemonics that get turned into those opcodes. MOV standing for move, right? Or read, meaning, one thing, and write meaning another. A high-level language uses English-like syntax. Although you could write a high-level language and that was in Russian or whatever. And algebraic notation. If you wanted to add two numbers in assembly, it would not look like A equals 1 plus 2. It would not be in algebra. Let me go and see if I can find an example. I haven't done this, so I'm not sure I'll be able to do it in 10 seconds. But add two numbers in assembly language. Oh boy. Come on, I saw you, and then you refresh the screen. All right, here's how you add two numbers. I would much rather type x equals 1 plus 2. Right? These are the opcodes. INT stands for interrupt, MOV stands for move, LEA, whatever. It's been a long time since I took a course in how to do this stuff. I've forgotten 99.999% of it. You don't need to know how to do this kind of stuff to be a great programmer. I'd rather just type in x equals 1 plus 2 than have to type in all that stuff. So the compilation process for a non-Java programmer, I just talked about it. You write a text file, a .c file or .cpp file or something, and then you run a compiler, and it turns it in to the machine language. Then you can send somebody that app or that executable or whatever. Source code compiles, makes some binary instructions, a machine language which the computer runs. It's not portable though, right? You can't take those zeros and ones and then put it on, different machine and expect it to work, right? And everything's a computer nowadays, right? Your car's has a whole bunch of computers in it. Your microwave's probably got a more powerful computer in it than what sent, the Apollo rockets to the moon, right? Your watch can be an iPhone, in disguise. Everything's a computer nowadays. And so then there's a thing called the Java Virtual Machine. I called it the Runtime Engine here. That's a generic term. I'm going to edit that and call it the so-called Java Virtual Machine. An engine just means a program that does something. not a real fancy, I mean, it's a fancy term. Virtual machine. Ooh, what does that mean? Why is it virtual? Well, good question. I guess because it's not a real machine, right? It's not something you pick up, it's just a piece of software. But it's the emulation software that takes that bytecode and runs it on whatever, turns it into different machine language based on what platform it is. So let's rewrite these notes just a little bit. The Java compiler takes the .java text file and turns it into, and I'm going to get the exact term because it might not be called bytecode. I may have given you the wrong term. That's a generic term for it, but yeah, bytecode. Woohoo, I got it right. Turns it into bytecode. Then the Java virtual machine, when you want it to, turns that bytecode into machine language and runs it. And do you care about all these details all that much? Not really. You don't have to know how to do these things. You just have to know that you're going to write a program and then you're going to run it, right? But it's nice to have an idea in the back of your head of how this stuff works. Especially if you're going to become a professional programmer and you need to know the difference between C++ and Java, how they work. In one of them, you make an executable file, an app, and you give it to them. And in another one, you give them an executable that's compiled for a specific kind of machine. Java's a little bit different, right? Source code, the compiler turns it into bytecode, and then the so-called JVM translates that bytecode to object code, the machine language that the computers run. I guess everywhere I typed in machine language, I should put object code, because that's what the textbook calls it. Textbook calls machine language, quote, object code. You can buy 100 different textbooks and they'll call the same things 50 different things. Similar ideas. Same concepts, but expressed slightly differently. I'm never going to give you a quiz where both machine language and object code were two different answers and only one of them was right. That would be really annoying. As a matter of fact, I'm not going to give you a quiz over chapter 1 at all. So the history of Java. Why was this language even invented? In the early 90s, even before the World Wide Web, people knew that you were going to start making smart appliances, right? Smart microwaves, or, you know, cable boxes that were actually computers, right? You know, to control your TV, or your VCR would be a whole computer rather than just, you know, a primitive device. So people thought that you were going to be putting intelligence into appliances. The next hot technology. You might have a coffee pot that's programmable, or lights, you know, that can turn on and off at certain times, or televisions that are run by an interactive device, a set-top box, TiVo or whatever. And so Sun Microsystems decided that if they could make a language that ran, one language that ran on any of those devices, then they'd be ahead of the game. Because otherwise, you know, your microwave would have a different chip than your TV would, and your TV would have a different chip than your car engine would, and so you'd have to write a different program to control each one of those in a different language and a different syntax. But with this virtual machine idea, you could write one language and it would be able to run on any of those devices. Now, it turned out that the big money was not in writing software for microwave ovens. Instead, somebody figured out how to make Java run on your own computer, downloading programs from the internet. Right? The internet became a thing like in the mid-90s. I mean, it existed before then, but, you know, people didn't have graphical web browsers before that. And that's when it took off. That's when you wanted to have 1 million different Java programmers. Originally, it was called Oak. I guess because the programmer looked out the window and saw an oak and he needed a name for the language, so he called it Oak, and then somebody decided that Java was a better name. I don't know why Java is a better name than Oak, right? But anyways, why not put that down just in case you ever want to do some trivia. Java was developed by Sun Microsystems. A company named Oracle owns it now. If you've heard about databases, you've heard about Oracle. It was designed to run on smart devices, you know, fridges, microwave ovens, cable boxes, you know, fridge, their example was coffee pots, right, and, you know, TV boxes, etc. Got turned into a program, or got turned into a technology that ran on PCs on the internet. And then boom, got super popular. Because you could write one program and then have it run on a whole bunch of different brands of computers. Before that, you couldn't. You had to have a Macintosh programmer on staff as well as a Windows programmer and stuff like that. At the time the book was written, I think Sun may have still owned it, so the book may refer to everything as being Sun. It hasn't been updated in a while since, you know, the 2012 and something. Advantage of Java. The same code can be run or written to run on many platforms. Macs, Windows, coffee pots. This chapter is great and all, but it means that we don't actually do any programming because we're talking too much history. We might just stop. Alright, so pseudocode. Quiz questions. What is pseudocode? Does it use precise computer syntax? Nah. Does it compile? No, it's not a language. It doesn't compile, but it is used when writing an algorithm. Java programs can be embedded in web pages, and such programs are called, well, if we'd read the chapter, we would call them applets. Nowadays, applets are not a thing. The browsers forbid applets from running because they were considered security risks. That's why we're not writing web programs. Now, you can write Java programs that run on a server to create web pages, but we're writing standalone programs. Our programs don't run in a browser. If you submit your own, for Pete's sake, this is supposed to be a PowerPoint for everybody, not just one particular class. Okay, forget this page. I should delete it entirely. All right, so why don't we write, we have a whole 10-15 minutes left, a little program of the sort that the first homework assignment may have been, if I recall it. So I'm going to launch good old NetBeans. When you installed NetBeans, if you have, it looks a little bit different. We've gone over that. That's because this is using NetBeans 8. We're now up to NetBeans 11. That's just like Visual Studio for C++, which is the 2012 or 23 version, and then when you install it for that class, it's the 2019 version. It's a little bit out of date, and I need to ask why we're using such old versions of it. Anyways, new project. This is Lecture C, I believe. So you can choose Maven or whatever. I would like for you to choose A and T if you can, but if A and T doesn't work, then do Maven. Now, if you're using a school computer, just choose Java, which is the ANT system. All right, let's call it Lecture C. What I would like for you to do, but you don't have to, is you see this thing down here that says Create Main Class? Now, if you're using Maven, you're not going to even see that. But if you choose that ANT option or the Java option on the old version of NetBeans, delete everything before and including that period. It just makes it easier for me to grade. You don't have to do that. But where it says create main class, delete the period and everything before it. And click finish. And if you were using ANT on your 2019 machine, or if you chose Java on the school computer, then it created a Java file. If it didn't, you're going to have to add one yourself, like this. It did not create my file. So if you're having to use Maven, you can come to Source Package, right-click, and do New Java Class. And then you give it a nice name, like Lecture C or something. And then you're going to have to type in one more line of code. You don't have to do this if it already gave it to you. Public static void main, parentheses, string, args. I think it's string. Oh, let me sneak a peek. Yeah. String, square braces, args, in parentheses, open curly brace, close curly brace. All right, now I'm to the same point. If you're having to use Maven, I would just kind of copy and paste this stuff, you know, and save it to a file so that you can always bring it back fast. Is everybody at this point, or is anybody having to catch up? Now, you didn't have to type all that if you're using a school computer, or if when you did file new file on ANT, it created your file for you. How's yours doing?
Okay, started clicking on that.
Awesome, awesome.
I
So
don't know what happened to it.
maybe all the laptops are working with Ant now. That'd be awesome. Okay, so let's create a program that, I don't know, like I said, calculates the inverse of the number. We kind of had an algorithm for that. We're going to ask for the number, and then we're going to get that number, and then we're going to calculate the inverse, which is just 1 over that number, and we're going to print it out. Now, since our application needs to accept input from the user, we need to use the scanner class. I should have made that uppercase S. So I need to make a scanner object. And this is one of the things that your code was missing. So when you go back to your homework, it's going to make a lot more sense after we do this second example. Scanner, capital S, SC, I just like SC, you could call it anything. You could call it input or something, equals new scanner, capital S, parentheses, system with a capital S, S-Y-S-T-E-M, dot, I-N, in parentheses, semicolon. And it's going to say, I don't know what a scanner is. We can fix that. I click on this, and it says add import for java.util.scanner. I think I already gave a great big lecture saying never just click on the error and accept it unless you know absolutely what to do. Specifically, never choose create class. Really bad idea to try to fix a syntax error by choosing create class. But adding an import, great. That's a great idea. When I do that, it adds this line to the top of my code. You know what, I don't like all these comments here to change this license header. I'm going to delete that. Alright, we have a scanner that we can use for input, but we haven't told the user what to type in yet. So we're going to do that. System, capital S, dot, OUT, all lowercase, dot, print or print line, parentheses, quote, enter a value for X, end quote, in parentheses, semicolon. Or maybe I'll just make it print so it won't go to the next line. I'm going to take the ln out, and I'm going to make it enter a value for x colon space end quote in parentheses semicolon. Now we need a variable to read their input into. Well, they're having more fun than we are. So let's create a variable. Why don't we make it a floating point number so that they can type in 1.5 or something like that? So we're going to have the word double. For now, you may as well make all your numbers doubles until you need otherwise. A double is a number that supports a decimal point. So it's a great type of data. Double space x equals, and now we need to read in the number. So we're going to use our scanner. And I know that this is a little bit of a, Greek to you. But if you've seen a programming language before, you kind of know what's going on here. sc.next, and then capital D for double, parentheses in parentheses semicolon. And this is the part of code that your homework was missing, is to let them type in a value. Okay, so we have a number. We can calculate the inverse. Double space, what are we going to call this variable? Why not just call it inverse? Equals 1 over x. And now we can print our results. System.out.println, parentheses quote, the inverse of x equals, end quote. And you Python programmers note you don't separate things with commas. I don't think you do. Might work. Plus x. Excuse me, plus inverse. I don't want to print out x. That's what they typed in. In parentheses, semicolon. Let's run the program and see if it works. I'm going to hammer and broom it to build it. My output window's hidden. Come back. It's taken a long time to build it because it's using Maven. Alright. It built it. It finally said build success. Great. I'm going to press the green arrow. Honestly, you don't have to do hammer and broom. You can always just go for the green arrow. I like to kind of reinforce. If it asks you to select a main class, go ahead. Remember permanently. You probably don't have to do that if you created it in Ant. Down here, it's going to ask me to enter a value for x. And 1 over 10 is 0.1. So our program worked. All right. I think we have time to write just a little bit more, and then we'll create our homework assignment. What is that? Oh, that's that day's homework. All right. We're going to ask for two values, and we're going to multiply them together. System.out.println, parentheses quote, number multiplier. We're just going to tell them what this program does, end quote, in parentheses semicolon. Then we're going to tell them what to do. System.out.println, enter number 1, or actually just print. I like using print so it doesn't go to the next line. Enter number 1, colon space, end quote, in parentheses semicolon. Let's let them type it in. Double in 1 equals sc.next double, just like we did last time. This is the line of code that lets the user type in the input. Now let's enter number 2. I'm so lazy, I'm going to copy and paste. I'm going to copy these two lines of code You just right click and choose copy or use the keyboard shortcuts. Paste them and change the 1s to 2s. Enter number 2. Double into equals sc.next double. Now let's calculate those two numbers multiplied together. Double space product equals n1 asterisk n2 semicolon. And then let's print the result. Capital S system dot out, not ERR, system dot out dot println parentheses quote, the product is end quote plus product, because that's the variable that we're printing out and this is the string that describes that variable. Let's test that one out. Enter value for x. All right, 2. 1 over 2 is 0.5. Enter number 1. I want to multiply two numbers together. 3 by 7. The product is 21. That was kind of lame. My output didn't have a space. I'm going to go back and modify my source code to put a space after the word is. Just to make it prettier. All right, I know you may not have gotten all this typed in, but I want to give you the description of the homework assignment anyways, and then I can print this out for you or bring the code back on the screen. So we need some homework. Here's what the homework's going to be. You don't have to type in the homework description because I always upload it. You don't have to take the time. But I'm going to start a multi-line comment with a /* and I'm going to end my multi-line comment with a */. Homework. Write a program that asks the user to enter the height and width of a rectangle. This is going to seem real familiar to Lindy because she saw the same homework assignment in Python, pretty much. Your program should calculate the perimeter, diagonal, and area of the rectangle. You can Google how to calculate these three things. If you get stuck, it's not a math class. Feel free to ask. Text me and I'll give you the formulas. Hint, diagonal is Pythagorean theorem. Okay, so that's the homework assignment. Just going to ask for a height. You're going to type in 10. It's going to ask for the width, which is 20, and it's going to say, okay, the perimeter is 60, and the area is 200, and the diagonal is 15, or whatever, right? And so the program should look like this when it runs. And they could type in 20. Please enter the width. And I could type in 10. The perimeter is 60. The area is 200. And the diagonal is 15 dot whatever. I don't know the last one. So it's not correct. Okay. That's what your program should look like. Does that make sense, gang? If you get stuck, ask me for help. Is this going to help you do the first homework assignment now that you know how to do the input and the output? What's the error there? Okay, yeah, you see that. Okay. if you're not done with the first homework assignment, homework 1, no problem. Work on it over the weekend. If you get stuck, text me for help. Who needs to see the source code back up? I can scroll back up. If you didn't finish typing it, that's fine, or I'll print it out for you. Nobody's asking for it. Alright, if you do need to print out, fine. I'm going to stop the recorder and create the Dropbox.